Hi, in this session, we are going to talk about stock span problem. It is a very famous interview problem asked in companies like Amazon and Google. So now what happens is that as soon as I tell you that this question is asked in Amazon and Google, you will try and look for an optimized solution, right? So what we will do in this discussion is we will first try to understand the problem and then we'll try to solve the problem irrespective of what is the time complexity or anything. We'll just see what is the first solution that comes in my mind or our mind, and then we will see how we can further optimize it. So what I will expect from you is that as soon as you understand the question, when I explain the question basically, first try and solve on your own. Just try the brute force approach. Don't need not come with the directly with the optimized approach. First try the brute force approach, and then we will see that how we can optimize that brute force approach, and then we will go ahead. Okay, so let me first explain the problem statement to you. So what the problem statement says that you are given a list of prices of single stock over n days. So here the list of prices is there. So let's say the stock is of any particular company. On the first day the price was 30. On the second day the price was 20. On the third day it was 40. Then we had 10 and then we had 60. Okay, and since it's an array element, I'll just put on the index as well. These are the indexes. And you have to find stock span for each day. Okay, so now the question is obviously what is span? So basically span is number of consecutive days before that day or before the given day when price is less than equal to that day. So basically span is nothing but number of consecutive days before that day when the price is less than or equal to that day. So this is one thing. Apart from that, what happens in this case is since there is no prior day to this particular first day, we will have the span as 1, and for all the days which is not having any day prior to it which is having value less than that day, the span will be by default 1. So let's just try to calculate the span for this particular list of prices and you will understand the thing better. Okay, so in this case for 30, as I said, this is the first day, we have span as 1. So let's say we're calculating span. So for 20 we can see that just before 20 we have 30. So for this obviously there is no such day for which price is less than 20, so we'll have the span as 1 again. And then we have 40. So as you can see that just before 40 we have 20, obviously it's less than 40, and then we have 30 which is less than 40. So the span is 1, 2 and 3. So 3 is the answer. And then we have 10. Just before 10 we have 40, again greater than this, so span is 1. And for 60, as you can see, we have 1, 2, 3, 4. All of them are lesser than 60. So the span is going to be 5. 1, 2, 3, 4, 5. Okay, so that is what is going to be span of this particular array. Now let's take one more example. Okay, so let's say we have 30, we have 20, 40, 25. Okay, so in this case what will happen is the span for this is 1, the span for this is 1, the span for this is 2, and what is going to be span for this? So I've taken this example to make you understand one point, that the number of days should be consecutive and should be just before that particular day. So in this case you can see that 20 is here, which is having value less than 25, but it is not consecutive and it is not just prior to it. Or for that matter, let's say there would have been a case when we had 30, 10, or for that matter 10, 30, 20, 25. So in this case again we have 20 which is less than 25, we have 10 here also which is less than 25, but again we have 20 just consecutive to 25, but 10 here is coming after 30 which is less than 25. So again I'm repeating, you have to take care of two things. I want to clarify this in your mind, that it has to be consecutive, the number of days have to be consecutive, and they have to be just starting from before this particular day. Okay, so in this case my span will be 1. Now explain the question. I would like you to take some test cases. Just try and come up with an approach on your own. Pause this video, try the question, try to find out the solution, and then you can just come ahead and see how we have discussed the brute force approach. So I hope you guys have tried the brute force approach. If you would have come up with the optimized solution, that's great. And if you would have come with the brute force approach, then also it's great. And if you haven't come with any approach, let's just try and see that what is the brute force approach. And I would like you to think that why couldn't you come up with that approach while we are discussing, okay? So let's say the brute force approach is going to be quite simple. So what is it that we can definitely do? So what we are going to do is we are going to each day and we are going to find out the span for each day. And how are we going to do that? So let's say I go here Here obviously since it's the first day, I'll just put the span as 1. So I go here, and since I have to find out the consecutive days prior to these days, so what is the simplest thing that I can do? I can just go ahead and check that if the price is less than this or not. So what I'll do is from 20 I'll go to 10. I'll check obviously 10 is less than 20. So I'll make the span as 2. Okay, so I come here, I check this and I check this. Okay, both of them are lesser, then obviously I'll make it 3. Now I come here, I check here. So as you can see, the 30 is greater than 5. So obviously there's no reason of going whole to this particular place, going back to this particular places or going back to these days and checking, because obviously we are looking for consecutive days. So here we just put it 1, and then we come here, we check again, we try and go back here. So we are checking for 5, it is less than 10, obviously the span becomes 2, and then we check here, it's 30. Obviously again there is no point of going further, so we make the span as 2. Similarly for 20 we have 10 and 5, we come here, we stop, so the span becomes 3. And for 50 we have 20, 10, 5, 30, 20, 10, all of them are less than 50, so the span becomes 1, 2, 3, 4, 5, 6, 7. Okay, so now if you can see, the logic is that from that particular day we will start iterating to the days before that, and the moment we get a day which is greater than this particular day, we'll stop our loop there and then, else we'll just keep incrementing. Okay, so if you try and write the code, I'll just write the loop part. Okay, so we will have a, let's say, result array, or let's say the span array, in which we are keeping the span. So we will keep the span of 0 as 1 by default. Okay, and then what we will do is we'll run a loop from I equal to 1 to n minus 1. For every I, or for every day, we'll initialize the span with 1, because 1 is going to be there by default irrespective of whether there is any consecutive day with less value or not. And I'll run a loop from j equal to I minus 1, and it will run only till j is greater than equal to 0. Okay, and I'll just keep on decrementing my j. In this loop I'll check if a of j is less than equal to a of I. I'll simply increment span of I. Else what I'll do is, if this is not the case, I'll simply break the loop, because as I said, we are here at a place where a of j is greater than a of I, then there's no point of going further, right? So in this case, let's say what happens is that we have I is equal to 0, 1, 2, 3, 4. I is equal to 4. Okay, so we make our j as 5. We start from here, obviously it's less than equal to 10, we increment our span of I, and then we go here. As soon as we see that it's greater than a of I, there's no point of going further, right? So what we will do is, if this is not the case, we will simply break. Okay, and we will close both the loops. So this is how we are going to solve for this particular problem. Now this is the brute force approach. Let's see what is the time complexity and space complexity. So as we can clearly see that we are using an extra array to keep this span, so the space complexity is going to be O of n. So we can actually reduce this O of n to O of 1. How is that going to happen? So what we are doing is, we are just, rather than keeping this span of 0 and storing the value, we'll simply print it. So here I'll just print 1. Here what I'll do is, we'll have some variable, let's say it's span. It's a variable, it's not an array. We'll initialize it with 1, and we'll keep on incrementing it here, and as soon as we come out of this particular loop, we'll simply print span. We are not using this value, so as we go further we'll see how we can use this value, but right now we are not using this value, so there's no point of storing it, right? So what we can do is, we can simply print this span for every iteration, so the space complexity becomes O of 1. And in worst case, what will be the time complexity? In worst case, what will happen, as you can see, is that it might be the case that the loop is in increasing order. In that case, the time complexity will be O of n square, because for every day, so let's say for this place the loop is going to run completely, for this place this complete loop will run, for this place this complete loop will run, so the worst case time complexity will be O of n square. So now we have seen the brute force approach, and now let's say we have to optimize the approach. So when you see this particular solution, one thing for sure is that this particular loop will run only till you find a day when price is greater than given day. Let's say greater than given day. Okay, so in this case, what is happening here is, let me tell you what I'm trying to say. Let's say we are at 20. So okay, so rather than just going across this whole loop and trying to find out that what are the days for which price is less than 20, why not we find out that what is the nearest day for which price is greater than given day. So in this case, as you know, the day is 30, right? So the day is 30. So 30 is the nearest day which is having price greater than 20. And if I know that, I can simply minus the indexes and we can find out that what is going to be my span for 20. So I'm repeating, I just have to find out that which particular day on the left is greater than this particular day. So in this case, obviously there is no such day. In this case, obviously there is no such day. It's going to be, for that matter, let's say 0th. In this case, we have just this particular day. In this case, again we have this day. In this case, we have this day. Again, in this case, it will be complete array, right? So I just want you to think, now the problem statement has changed a bit. So let's say the problem statement now is to find out the element, or let's say the nearest element on the left, which is greater than given element. So I hope you have understood things till now. If you haven't, maybe you can just repeat what we have understood till now, what we have tried to understand till now. I would really strongly recommend you that make sure you understand in each and everything before you proceed further, because if things won't be clear, you won't be able to come up with an approach on your own. So just first try to understand what we have talked till now. Try to come with an approach on your own, and then we will see, we will discuss that how to write this particular approach, okay? So I hope you tried the problem. So what we boil down to is that we have to find out which is the nearest greater element on the left. Okay, so what I'll do is, in this case, let's just see a pattern, and that will help us in deciding that how to go further. So in this case, for 65, anytime the span is going to be 1, right? For 10, the nearest greater element is having this index as, so let's put the indexes, is having the index as 0, right? So as soon as we find the next greater element, the span is going to be index of current element minus, let's say, greater element index. Okay, so in this case, it's going to be 1 minus 0. So the span is going to be 1. So in this case of 20, the greater element is 65. So the span is going to be 2 minus 0, 2. For 30, it's going to be 3 minus 0, 3. So as you can see, we are finding the next greater element. That means that all the elements in between are less than 30. So we just do the subtraction from that index. For 10, it's going to be 1. For 5, it's again going to be 1. Okay, so this is how we calculate the span. We just find index of nearest greater element on the left, and we just do the subtraction from the current index. And in case, let's say there is a scenario in which we have, let's say if there would have been something like 1, 2, 3, 4. So in this case, if let's say there is 4 and all the elements on the left of 4 are smaller. So obviously in this case, let's say we consider that if there's no nearest greater element, we'll return the index as -1. So in that case, what will we do is we'll have index minus -1. So that will make us index plus 1, right? So in this case, index is, let's say, 0, 1, 2, 3. So it will be 3 plus 1, 4. Okay. So in case there is no nearest greater element to the left, we simply return -1. In case there it is, we simply return GE, which is the greater element. Okay. So again, I'm repeating, the question is how to find the greater element. So I'm just using this whole nearest greater element to the left as greater element to keep it small, obviously. So okay, so let's just talk about greater element. Okay. So one thing I observed is that, let's say if it is 65, 10, 20, 30, 10 and 5. So if you see that for 10, it's 65, for 20, it's 65, for 30, it's 65, for 30, it's 30, sorry, for 10, it's 30, and for 5, it's 10. Okay, so now using this, what I just thought is that maybe if we are using some extra space, that is going to help me optimize my time. So what I'm going to do is, let's say I'm just going to keep 65 in some space. We'll see which data structure it is, okay? So we keep 65. Now what we do is that we move to 10. We see that if 10 is greater than 65. So initially what we were doing, in order to find the previous greater element, we were moving to all the elements on the left in this array. So I'm not going to do that. I'll just compare with this particular thing, with this particular space, okay? That will save us time. We'll see how. So in this case, we have 10. We compare it with 65. Since obviously 65 is greater than 10, then for this it's 65, or let's keep the index, it's 0, okay? So now what happens is that for any element after 10, the greater element could either be 10 or it could either be 65. Do I have any other option? No. So if there would have been 5, then for 5 the greater element could be 10, right? For 20 it's not going to be 10, it's going to be 65. So right now at this particular point we have just two options, that it's either the current element or this particular element, okay? So what I do is, what I'm doing is that for finding the greater element, I'm not comparing with this set of numbers, I'm comparing with this set of numbers. So I just keep 10 in this space, okay? Now what happens is that I check for 20. Is 10 greater than 20? No. Is 65 greater than 20? Yes. So for 20, the greater element is 65, the index is 0. Now one thing I want to think is that, for if I have to calculate the greater element for all the elements from after 20, is there any possibility that for any element out of these particular elements, for any element, the greater element is going to be 10? No, that is never going to happen, because we already have an element which is 20 and it is greater than 10. So there is no point of keeping 10 here. So I remove 10 from here and I put 20. Okay, so again, for all the elements after 20, what are the options? That either the greater element is going to be 20 or it's going to be 65. Next, let's proceed further. So now we have 30. So for 30, the same thing happens. It's greater than 20, so there's no point of keeping 20 here. I remove 20, I keep 30 here. Obviously, let's say the index is 0 for the greater element. Now we have next thing is 10. So for 10, we check with 30. 30 is here. So now we see that 10 is small, right? So if there would have been 20, for 20, 10 won't be the greater element, 30 will be the greater element, right? So we cannot remove 30. But since 10 is there and there's a probability that for all the numbers less than 10, 10 could be the greater element. So what I'll do is I'll keep 10 also here, right? I keep 10 also here. And now I move here. I check 5. So let's say for 5, 10 is greater element. Yes, 10 is greater element. So what I'll do is I'll keep the index here. I'll update the index. For 10 it's going to be 0, 1, 2, 3. 3. For 5 it's going to be 4. Okay, and I'll keep 5 here as well, because again, for if there's any element which is less than 5 in this particular area, then for that the greater element will be 5. Okay, so now next what we do, we check with 5 is greater than 20. No, that is not the case. I remove 5. 10 is greater than 20. No, I remove 10. Now 30 is greater than 20. Yes, so I update the index as 3. Yeah, I update the index as 3 and I keep 20 here. Okay, so there is no any element outside, right? So as you can see that rather than going through all the elements again and again, which we did in our brute force approach, we somehow used extra space and saved some amount of time. We will calculate the time complexity and see how much time we have saved. But as you can see, the time is saved. Now let's say there would have been something like 60. Okay, I'm just trying to wind it up. For 60, what would happen? We check with 20. Is this the one? No, cut it. So these are not there. These are not there in this particular place, right? So we check with 30. Is it there? No. We check with 65. Yeah, is 65 the element? Yes, 65 is the element. And if there would have been 70, then even 65 would have been removed. And we got to know that there is no element which is greater than 70. Then in that case, the -1 will be written for the greater element. So now there are several things here. Number one, how do we calculate the complexity, time complexity, because we have just done some operations, right? And the second thing is what data structure to use, because as you can see, we have done so much of removing the data, putting in the data. And if you see it carefully and if you know the stack thing, or if you would have already known the stack thing, because we have this problem that which data structure to use. As you can see that all the time what we were doing is we had one open end. We were putting data here, we were removing data from here. We were putting data and we were removing data, and we were always removing and putting the data from the top. So, and obviously if you know that which particular data structure for is best for this, then we have something called as stack. So we know this is our logic, and we have to implement this logic using stack. So we will implement this logic, and then we are going to decide the time complexity. Okay. So let's say I won't get into too much operation of push and pop. How is that happening? I'm assuming you already know that. So let's say we have a stack. Okay. So let's say we have a stack. So initially what we did, we simply pushed 65 in the stack. So I simply pushed, let's say this is R, simply push stack dot push R of 0. Okay. Now 65 is there in the stack. Okay. So now next what we have to do is for I equal to 1, I less than n, I plus plus, what I'll do is I'll compare. So if you see that there wasn't a single comparison, so when we were here at 20, what we did was we first compared with 5, then we compared with 10. So we are comparing it again and again, or if there would have been 40 here for that matter, then we would have compared with 30 as well. So we know that just one if won't work, we will need loop here. Okay. So what I'll do is I'll keep while. So we were always comparing from the top, right? So we check that while stack dot top, if it is less than equal to R of I. So we were always checking, right? If it is less than equal to R of I, then if that was the case, we will continuously removing the elements. But we also have to check that it might be the case that we are removing the elements and we just all the elements are clear. So we have to ensure that and stack dot is empty. I'm not implementing this in any language. You can implement this in C, C++ or Java depending upon how the syntax goes. So I'm just trying to write a very generic code, okay? And stack dot is empty. So stack should not be empty, right? Obviously in that case you'll get runtime error if you're trying to do that. So what happens is that we check that if stack dot top is less than equal to this particular thing, what we did, we simply remove these elements. We simply do st dot pop. Right? So we simply remove the element. So as you can see, we are not updating our span till now, right? So we have to keep our span as well. So the span for 0 is obviously going to be 1. Now let's say, as we saw that there were two situations. Number one is that there is no greater element on the left. So what we will do is, how do I know that there is no greater element on the left? So if we are trying to do the operation and we saw that if this stack becomes completely empty, which shows that there is no element on the left. So in that case, we'll check that if stack dot is empty, then span of I will be I plus 1, and else it will be simply, so here we are storing the indexes actually. So I'll just do is, what I'll do is I'll store the indexes. I'm so sorry, it has to be indexes. So it has to index, I'll just remove this. It will be stack dot push 0. So in this case, what will happen is I'll check if stack dot is empty, else it will simply be, okay, in this case it will be R of stack dot top. Okay, so in this case stack dot top is the index and R will be obviously the value at that index. That's we are going to compare. Sorry for the mistake. What we will do is, if we check stack is empty, we simply do span of I is equal to I plus 1, else span of I is going to be I minus stack dot top. Okay, now what we did, what are the operations that we did? What we did, we checked, we are comparing the element from the stack dot top. If it is lesser than this, we are simply popping it up, and the moment we find that there is a element, or if there is no element, accordingly we calculate the span. One more thing that we have to do is we have to push the current element or the index of the current element. So what we do is, we have for here, while is from here to here, and then we have if stack is empty, this works, else this works, and the other thing that we have to do is stack dot push I. Okay, so this is how it's going to be. So this is how the program will work. Now let's see the time complexity. So if we try to see the time complexity, one thing I would like to tell you is that though we have a while loop here, if we see the number of operations, you just saw that each element here was pushed in the stack exactly once and was taken out from the stack exactly once, right? So this particular thing, this whole push pop thing will take extra time of just O of n. So the time complexity obviously for this loop is going to be O of n. So the total time complexity is going to be O of 2n, which obviously is O of n. Okay, and if we talk about the space complexity, obviously the space complexity, as you can see, is going to be O of n. So this is how we can solve this particular problem. So one thing I try to tell you is that you need not, always decide which data structure to go for first, or need not just directly go to the optimized approach. Maybe first try to come with the brute force approach, try and see some pattern, try and come up with the solution, and then try and see which data structure to use. So it obviously more you practice, these things will become more clear to you. All the very best. Make sure keep coding.